No, but I really need to do that. Like, I don't keep notes. Yeah, but I want to.
I finished my degree. I don't keep notes either.
No, no, like after the semester, I don't even have notes to revise on because I don't do it that way.
Well, as in I keep the notes that I was given.
No,
If you make notes, I don't really
digital.
make notes. No, I keep all the paperwork that we were given because that's basically a degree. So, as in, like if I have handouts of entire modules, I'll keep those handouts.
Yeah.
Because that's probably infinitely more reliable than the scraps I have.
Yeah.
But, yeah.
But
You're saying you need to do that to keep because you don't keep notes.
Oh no, I want to get each module and get a small notebook and then summarize the whole module in that notebook.
You just want to create journals.
Well,
50 years from now, when they're like the history of Ali Fazanafar and his rise to scientific stardom.
Journal. Hey,
and you're like, we found it, and then you'll be on like those shows and they'll be interviewing.
My children.
Yeah, it was like we tracked down some of Ali's former housemates.
No, but dude, it's so useful. Like,
no.
And I don't mean useful to read it. It's useful to write it organized like that. And then, like, when you think of it, like, it's sort of like the what do they call it? The mind. It has a name. The technique. Like a mind.
Not mind map.
Yeah.
Oh.
Yeah, something like that, but not as literal as they take it as a place where you go. I mean, like when you write it, then you remember it. Yeah, a mind journal, which is just memory. But yeah.
I think that.
Have you ever tried to do that?
Yes.
Were you successful?
No, because
you don't have a place that you go regularly that you look, every bit of it.
Oh no, it's not a case of. I don't mean this in the sense that my mind is so fast. It could just be that my body's too slow. That when I have thoughts in my head and I work through things, it happens at a rate that for me to write it down or try to express it physically, as in with my body, just becomes so slow that, like, in my head I'll already come to some conclusion that I won't remember the first thing that I started with to write it down. So it'll all be there in my head and it'll make sense.
No, but just memory feats, like remembering like a deck of cards in order.
Yeah, how do you mean?
Like, I give you a deck of cards, and then you have to memorize the order in which they are.
Yeah.
And only by looking at them once. And then or like by playing with them for 5 minutes.
Kind of create...
Yeah, have you heard of the mind...
They're like memory
TV show
techniques.
uses it a lot.
Huh?
Sherlock.
Oh, I haven't seen that.
Yeah, sure.
I've been meaning to, but I haven't.
Yeah, it's a mind palace.
Okay, journey through the mind.
Yeah, exactly. Yes, that one.
Blah, blah.
Yeah, so like...
Do you guys want some chocolate?
Oh no, I'm okay. I'm cutting down.
Green box.
Apparently,
it's not a box.
They are the leading cause of heart attacks. So enjoy.
Chocolate.
Yeah, apparently sweets are worse than fat.
But it's dark chocolate. It's like
what I read online, which is not very reliable.
Yeah, but it's...
I know, it's quite good.
You don't want
A crumb just fell out, so I'll consume that.
Consume it. Oh god. Consume. Yeah, so we're talking about mind palaces.
Yeah.
Is
that the Sherlock thing?
No, that's from Inception. It's just like, because they keep everything locked away in a memory safe.
That's weird. Like, I'm like, what the hell?
Are you guys warm enough, by the way?
Mm-hmm.
Yes. But like, we should be going. We've been here for like 3 hours.
Have you?
Yes.
Oh.
Well, whenever you want to go, you're welcome to stay for
Just say
longer.
whatever you want.
Sorry?
You say whatever you want
Oh,
to say.
no, I'm fine. Yeah.
Fine.
When you guys, it's nice having you over.
So yeah, mind palaces. I've been looking online. It doesn't like it's sufficient to memorize like weird things like
Maybe if it works for you, it can.
Yeah, or like names of things or something like that. I haven't done it though. I'd like to.
Order of the Planets.
Yeah.
I never learned the acronym.
I don't know. I don't know the order of the
like
planets.
My very efficient
memory
just seems
functional. No?
I don't know what it was, but I just learned the order of the planets as it is.
Did you?
Yeah. As in for me, that
Really?
I don't mean that in look at me.
It's just. It's interesting how some people's brains can do that and other people's can't.
Well, for me, it just seems that. But if I learn another way, if I learn something else in its place, then I haven't remembered the names of the planets. I'll just remember what letter they begin with. But if I remember the actual names of the planets, then I'll remember the names of the planet. Like, for me, it just seemed that. But now I need to learn 2 sets of information, whereas it's easy to learn one. Well, like, I can't remember what the acronym is. But I can remember what the.
No, I don't know the acronyms. The only thing that I know is that when we were learning the Arabic, like the verbs, no, not the verbs, the like his, her, ours. What do they call those? Yeah, those.
Pronouns.
Yeah, those. You used your hand, left hand, I think. Yeah, so you got 14 of them, right?
So
and you've got 14 bits on your hand as well.
Really?
Yeah, you've got 1, 2, 3.
You
got 4. I was like 1, 2, 3, 4. I've got 12.
I'm used to the
13,
creases.
14. Yeah, the creases. That's what I meant.
There's 14.
Yes, like 1, 2, 3, 4, 5, 6,
Well, I guess
7, 8, 9, 10, 11, 12, 13, 14.
Oh, okay. So I'm not going to say in Islam, but a lot of Muslims, we have this thing called tasbih. You know, like rosemary beads.
Okay.
No, rosary beads. No, rosemary.
Tasbih?
Yeah.
Yeah.
So rosary beads.
Yeah.
A lot of Muslims, again, I'm not going to say if this is Islamic or not because I don't know. It could just be a cultural, traditional thing. You count, instead of rosary beads, you count the notches on your finger, on your fingers, because that's 4. As in, because we took the tip as well.
Oh, okay.
So that's why I'm used to 14 is 20.
Yeah,
And then you make the thumb into 4 as well. Yeah.
Okay.
And then you can.
No, so you have like you've got a male that is singular, there are 2 or there are more than 2. A female that is singular, 2 or more than 2. Shit, where was the rest? And then there was oh wait, okay, so no, okay, so right, so it's females present who are no, there's males present that is them, like you, or you two, or you many, or females present, you two, or you many. Males not present, him.
Gosh, really?
Yeah, those
That's
2
really
or those many. Females not present, them, her, those 2, that many people, or it's me, or it's us.
Me not present.
Yeah. It's me and us. Yeah.
That's amazing.
I think it was that. It was
I don't know. You'd have to go through this with me.
What?
I'm lost.
I know what wait. So I remember. I don't know. It's hova homo hom.
How does it relate to your fingers?
It's hova homo hom. Kia homo hona. Anta antoma antom. Ante antoma antona. Ananahno.
So really, it's just the thumb that's a special one.
Yeah.
Okay. No.
Yeah.
Mine's palace.
Did you say that's Arabic?
Yeah, that was Arabic. Those are the 14 Arabic pronouns, which was why I'm saying it's like really, mind bending.
Yeah, wow.
Arabic, the last mind bender.
The last mind bender. Oh god, wow. I just used that. The turtle lions.
I know. I've never seen any of it.
Oh, the lion turtles are the energy benders, and they bend minds and stuff. They can give bending to people.
Yeah,
Avatar.
I haven't seen it.
Oh my god.
I haven't seen it.
I thought you were like movie person.
It's an anime. I like anime. I do like anime.
It's an anime. Oh shit! I actually do like.
No, the Avatar is the there's the blue
people.
Alien.
Oh no, not that Avatar.
There's that Avatar. Then there's Avatar: The Last Airbender, which is a cartoon.
Oh, you didn't know this? Oh my god!
But then there's Avatar: The Last Airbender, which was the film, which people apparently don't speak of.
Yeah, no, that's like in the closet.
Yeah.
So it's what? What's a mind? What's
Airbender? It's basically about 4 nations, and there are airbenders who can manipulate air, waterbenders who can manipulate water. It's basically telekinesis, but with these elements.
Yeah, but with fire.
But then everything changed the day the fire.
And they should attacked.
Apparently, that's like the prologue of the series. Like,
yeah.
There are these 4 nations.
And then Earthbenders, Earth.
And who invented this?
It's an American anime. So anime is traditionally Japanese, but Avatar's an American anime. I have been meaning to watch it.
It's pretty nice. And then there's a new one.
The Legend of Korra. Apparently that's really cool.
Yeah, it's good.
I thought anime is just the word that we use to describe all Japanese animations. So what do you mean when you say
It's a style of
animation.
Yeah. Okay,
so it's in the same style, but it's made by Americans.
So like the artistic style, or yeah. And the thing with, again, you get kind of kiddie cartoony ones, but you get really mature themes.
Yeah.
And so,
like Mindbenders.
They can be mind bending. Like the first anime I spoke.
Sorry, do you guys want to eat toast or anything?
I'm okay. Yeah.
I thought about eating. Do you guys want to order anything to eat?
Yeah, no, I'm right.
Yeah, I'm okay as well. You can order, and I don't think we'll be. I'll be here for long.
Yeah, sure, that's fine.
Yeah.
Yeah, it's cool.
Feel free to order.
Huh?
Feel free to order.
Yeah, no, but I would only order really with you guys because otherwise, they, I'd have to buy quite a lot of stuff. Yeah.
Oh.
But no, that's not to incentivize you. I was just wondering if you guys want to
10 portions of prawn crackers just to make up that minimum requirement. Minimum spend has to be.
I've had so many cheesecakes because of that. Because you order and then I'm 8 pounds.
Domino's?
No. Domino's ends up being 20 pounds, whatever you buy.
No, I don't know. Who gives cheesecakes?
Everywhere, all these little restaurants on
cheesecakes
Just
are
Eat.
Awesome.
Yeah.
I didn't really go into cheesecakes until uni. Then I appreciated cheesecakes.
Really?
Awesome.
I was like, wow.
No, I wasn't into cheesecakes when I was 11.
Cheesecakes are awesome.
They're dangerous though.
New York cheesecakes.
Yeah. Yeah, but they're so filling and they're so yummy and they're so satisfying that you just want to eat the whole cheesecake from them.
No, but if you do that, then you won't like cheesecakes anymore.
I don't crave cheesecakes the same. I've kind of quite.
Yeah, no, I've done that before. You go and I remember this place that was near my house in Tehran, and they used to sell these amazing cheesecakes. I was like, can I have a piece? It's like, no, we just sell them in full. Whole. I was like, oh man, fine, just give me the whole thing. Yeah. And then I'd be in my home in the corner of my room.
It's like other people turn up to some social event with their box of pizza, and then you're there with your box of cheesecake, and you're like, you open the box, what pizza did you get? It's like, cheesecake. It's like, oh, what an iranian, honey. It's got cheese on top of it, but it's called a pizza. It's like, no, it's a cheesecake.
Oh my gosh, wow, you got sugar and everything. Wow.
Oh my god.
Cheesecake, or was like, oh shit, you topped it. You got the whole cake. It's amazing.
It's like, can you dip the crust? It's like, it's cheesecake.
It's cheesecake.
There are no crust. It's just cheesecake.
Oh god. No, but I really want to start making sushi.
I like sushi.
Oh wow.
Yeah. I remember I was in South Africa and there was this chef who was making sushi. We were at a sushi bar, and Precious was saying that in most African countries people.
That's not her name on Facebook.
Yeah. She was saying that they don't eat they don't like seafood like prawns. They like fish, but they don't like prawns and sea bugs. Basically, South Africa's a bit more, but still the native population.
Where was she referring to?
Most of African countries, yeah. And then, I think mostly she was talking about southern and eastern Africa, to be honest.
Is that an Islamic thing?
No.
Okay.
No, it's just, they're like, ew. That it's not part of their culture. And, so I asked the sushi chef, who was, native as well. I was like, so have you, ever had sushi? Do you like it? He was like, I have never had it. And she's been doing this for 8 years, and she's never had what she does for her job.
How do you know it's right? No one's sued me yet.
Yes. Oh yeah, they don't give. I don't think she was that. It wasn't that fancy a place that they would give you that stuff that could kill you. So yeah.
What?
No, we're trying to see. No. We're looking at your plate.
Oh. Jeez. Toast and no.
It's like cheese.
That's just lots of
cheese is crust.
Like cottage cheese.
It's just. I forgot how to word it. Not mayonnaise, not butter. The other one, margarine. It's just loads of margarine.
Okay, it was just the lighting.
The lighting has changed your food.
It looked white, so I thought it was cheese.
Hey.
Cheese.
Yeah. So, yeah, I was wondering what is the wave function in terms of time. I mean, if you describe it in terms of time, and it's space independent, then what does that represent? The probability that the wave function will be measured to be at time t.
But isn't it then you fixed the
Space.
the point? Yeah, you fixed the space.
Mm.
So it's the wave function going through that point.
Wait,
Isn't that what? So
can you fix the space?
if it's a
Can
standing
you fix
wave,
the time?
if it's a standing wave,
You can't fix the time. No. Okay, but a space
No, no,
independent. Right. You
so
need.
time independent
What are those?
means. Isn't that going to be a standing wave?
But this is yes, it would be a standing wave. Like they have a name. What are they called? Stationary states.
Mhm.
Yeah, but stationary states are stationary in. What are they stationary in?
Well, as in, isn't it?
They're
It's
in-
technically still there, but the whole thing is
It's predictably moving.
stable.
Yeah,
kind of
stable.
thing.
Yeah, okay.
Oh, yeah, okay, not stable because you've still got different. But yeah, as in,
Yeah, so you haven't fixed the position of it now.
yeah. So if you let time run on, the wave will stay as it is in a stationary state.
Uh-huh.
Or it will it? No. If you let time run on, then you add the time factor, then it starts oscillating. But it will oscillate predictably, I guess. But as in it will, its position.
Time independent.
Yeah, its position won't be more than like a certain. A certain space. It can't span any more than a certain space. It's yeah. I think they are usually sines or cosines. Yeah.
Isn't it? It's a standing wave.
Yeah, I guess.
Because when it's time independent, you don't have the phase factor.
Yeah.
So you've just got kx as the argument.
Yeah, but the thing is, it's when you describe it and when you separate variables, and then you have the time wave function and you've got the space wave function. Then what happens in those is that the space wave function describes the space as if it's frozen in time. Ish. No, actually, it's not even that. It's as if it's frozen at time 0.
Oh yeah, it's just whatever time it is.
Yeah, whatever.
This is how you would describe it.
Yeah, exactly. So, yeah. So if you wanted to do the other way,
That's what you represent with energy.
Yes, but the problem, the problem that I can't figure out is that how would you describe the Hamiltonian to go about it? Because the Hamiltonian is usually described through kinetic energy, which is okay. I guess you could describe kinetic energy.
It's mathematically has to be possible.
Yeah.
I think. I'm not going to force that, but I think.
No, I think because I think it is possible.
If we're kind of again tying this into the whole, well, if energy is the one constant of the universe, well, we say C is a constant, but then if we're saying C is also a natural unit, because as I was saying, like all the different quantities are measures effectively of the energy state of the universe. And with entropy, we always say it fits against time. We differentiate with respect to time.
Yeah, so if you do it with respect to space,
then part of me thinks that, well, yeah, you integrate back and then differentiate with respect to space.
Yeah.
So we could come up with a whole system
based on that quantity.
It's the same kind of thing, just
looked at
instead of looking at from the perspective of against time, we're looking at against the perspective of space.
Yeah, exactly. And then you would have a new anti-velocity. I don't know what do you call that thing, dt by dx. Whatever you'd have that, and based on that, you could quantify energy.
But the thing is, so I presume we do it. The system we've built again it's based on our observations and confined by observation because we typically do things against time because we were saying that we're used to perceiving time as kind of almost a constant. That's why we do things with respect to time. So it might be very counterintuitive, or unintuitive to do things with respect to space. But I wouldn't say it's not possible. It's just very abstract.
Yeah, it's just
But then the thing is, what if it is not possible and time is a very unique... I think what I'm getting at is that this should be tried out to see if a system can be... If a system can...
If it can, then it sort of starts to hint on the fact that there might be other dimensions of time.
Yeah. Well, that's what I thought when you said. Well,
time. What if it's just a magnitude? What if our experience of time is just the magnitude? Because we haven't.
We have our bodies built that way.
A magnitude.
Well, or just as in that could be one explanation. It could just be that because we are not sensitive to time on that level. So we're sensitive to space being split up into 3 dimensions, and it could be that because maybe we're going so fast through time and relatively slow in space that we are adapted to perceiving spatial differences across, X, Y, Z. But like you're saying, time could have these different components and different sub-dimensions, so to speak, that if we were to say our whole civilization, managed to get subluminal speeds of light, or as in we were capable of going very close to the speed of light, and our society lived like this, and all our daily experiences were sort of at relativistic speeds, or velocities, I should say so. And if we carried on living like that, and say thousands and thousands of years and so many generations, and say we went back to, because I'd say now we're largely dependent on technology, that we've stopped naturally adapting to things, or we don't do it as much, and say like we're going back to natural adaptations coming into play. What if we start becoming adapting because we perceive time so slowly, relatively, once we're going at relativistic velocities, we become more sensitive and aware of
as we go faster.
The differences in time, etc.
But that's impossible.
Is it?
Yes, because then you would have to be able to tell how fast you're going with respect to your surroundings, and not just only the acceleration.
Yeah, but that's the thing. I wouldn't say it's impossible. It could be
maybe like when you see stuff going by a certain, in a certain way, your body would sort of speed up your clock.
Yeah, no, but that's what I'm saying. So say we adapt to that. So we're adapted to classical Newtonian, what we deem as classical. And say we live in a relativistic world, and that we've become accustomed to that.
Yeah, okay.
Then would it be the other way around instead, that we're more sensitive to differences within time? We can kind of move through time. It seems very unintuitive.
Yes, but I think what you're sort of hinting on is that you would sort of have infinite dimensions of time. Now, bear with me. What I mean by that is that you would each dimension of time would have a certain speed, and depending on how fast you're going, you would.
Quantized.
Yeah, exactly. And depending on how fast you would be going, you would experience time along one of these dimensions. Dimensions meaning group. So if you're going at speed 20, you experience the world, at a certain speed, the world that, is not moving relative to you. And if you go at speed 30, you experience the world in a different dimension, which is time, that is, thinking of dimensions as just sets, So,
it's kind of what we do anyway.
Yeah. It is.
Oh,
it is.
With spatial.
Yeah, in reality, it is like that.
Have you went that direction? She went off in that direction, so I'm going to give her a Y coordinate.
Yeah, exactly. Something else.
That person went off in that, so I'll give them Z.
So you think time is infinite dimensional rather than just?
As in technically, surely you could say that's with spatial stuff, but with the 3-dimensional system. We use polar coordinates. We can use polar. So if I were to say, if I go straight forward, and we'll call this the x plane, then you could say my motion is described as x. But say I went 1 degree to the left and went in a straight line, you could effectively call that another dimension. Yeah. And then if I went another degree, that's another.
Yeah.
And because if we're going to say we can infinitesimally split these degrees up, you could say there are infinite number of spatial dimensions. And then we came up with, you could say, the x, y, z coordinate system to describe any position, and that's kind of where vectors come in. So
that's good.
A vector will break down. So if I went off in one direction, you could say that is a dimension itself.
Yeah.
But according to Cartesian coordinates, we can
not
represent his motion or her motion in x, y, z terms, or we can even use polar coordinates. So we've come up with a three-dimensional. We call it.
No, the problem still lies there, and the problem is that the way that the time is split depends on the magnitude of velocity, and the magnitude of velocity doesn't depend on direction.
But what if we curve? If say I took a curved path through space, then you could say relative to me, to the person going to the observer going along that path, you can effectively make that a straight line, and you just bend everything else around.
Yes.
So as in, say I had a grid, and instead of going and say you've got corners A, B, C, D, say I kind of went on a curved path from A to somewhere between B and C, and it's not a straight line, but I take it curved. But you could kind of shift space along
to make it look straight,
and make it straight for the person going along that path that the rest of space has walked, but it's straight along that person's dimension, and because that's straight, you could describe that as a dimension.
Yes, but then you'd have to re-describe everything else.
Exactly. So surely it's just a coordinate system by convention. Like so if I described a straight line, say I had x, y, z coordinate system, and I went from the origin to 1, 1, 1, as in 1 along x, 1 along y, 1 along z, then you could say, it's just a straight line. You could just describe that quite simply with x, y, z coordinate system. But say I took and say I did that at a velocity of 1 unit per second, then you could say, well, you could describe my motion as plus I plus j plus k t.
Yeah.
Yeah, say if I went at 1 unit per second.
Yeah, okay.
So after 1 second, he'll be at 1, 1, 1. After 2, he'll be at 2, 2, 2. Now, if I took a curved path, then you'd have to describe it with different orders. That's the thing. So as soon as it's curved, you change the orders. So you could say with higher orders, you're wrapping dimensions up.
To make it correspond to three dimensions
in this coordinate system. But if you wanted to keep everything on just on a linear order, you'd have to keep on to have a curved motion. You'd have to create
infinite dimensions.
Effectively, you'd be looking at infinite dimensions to keep everything on first order. So if we are going at relativistic speeds, we could describe our temporal coordinates in terms of t squared.
Yes.
T cubed.
It's quite cool. Wait. There are temporal coordinates. That bit. I get the bit about turning space linear would mean, giving infinite number of dimensions, as in, like, for example, you want to go on this line, instead of, giving it the squared and everything, you can say it, depending on where you are, you're on a different dimension, you're on a different line pointing in a different way. But, and we describe that in terms of TD squared and whatever. And, relativistically, as in time, we also do that, and we do that through the Lorentz transforms. And
yeah, you still transform, but we do proper time according to the static, to the observer.
Yeah, exactly, the origin, that would correspond to the origin in Cartesian coordinates, to your reference point, or whatever. You know what I mean?
But that's the thing, though, isn't it? You're relative to someone who's not moving. So you still get transformations. We still get transformations in both time and space. So, kind of by symmetry, not like supersymmetry, just general symmetry. If we have So on a classical level, looking at relativistic speeds, if we make transformations of both space and time this way, then kind of by symmetry, you would expect the same thing to happen the other way. Because effectively, this is all I'm doing. That if we're saying at our everyday velocities, our passage through time is like if we take this as normal passage through time and normal velocity, then if we go towards relativistic velocities, we'll say our passage through time is. Oh, actually, no. Okay, we'll measure it out of c. So our velocity now on everyday motion is very small compared to c. Through the conservation of, if we're saying about the 4-dimension thing, that therefore our passage through time is relatively high compared to, as in close to c. And then as we get faster in space, the distribution shifts from low speed now to high speed in space, and then high speed in time to low speed. So it's just an inverse proportion.
Yeah,
so there's a symmetry there of sorts.
Yes, but how can I'm thinking of how can, if other dimensions of times exist, then how can we bring that out?
But no, it's like I was saying with space, you can represent as just one whole dimension as a magnitude, but that we just differentiate along x, y, and z.
Yeah, exactly.
Rho,
but then again, we also define speed in space.
Yeah, as meters per second, but you could do it as kind of almost
anything.
Could you flip it the other way around?
Anytime, yeah.
Because like you were saying, if we're doing dt by tx, we could just flip everything around, and rather than so this is what I was saying, that with our intuitive daily lives, we do things, we measure the rate against time, because we see things happening as a function of time. But if you think about it, you don't inject a second into a system and advance it. You just, as far as we're aware, we just leave it.
So I mean, okay, so let's.
Sorry.
If no, sorry. So if other dimensions of times are there, then there must be a way to look at them, right?
Yeah. Theoretically, I would say.
Yeah, but we'd need to be built. I don't know. Well.
Oh no, not us. Like we'd have to have something to be able to look at it.
Yeah,
it's physically possible.
Things would change distance.
Like this is relative to our perspective.
Yeah. So so we have to start from there to see how would it look like?
Yeah. There was that nice MIT applet simulation that you start off at classical velocities, and then you can increase your speed towards relativistic.
And it looks different. Yeah.
And it shows you what a 3D transformation, and you get the Doppler effecting and Lorentz contraction, etc. It's quite cool.
Yeah. So if you would have other dimensions in time, I don't know why I'm thinking of 3.
Just because it's intuitive.
Yeah, but
come up with a system for space.
What can we do in space that when we do it in one way, along one dimension, doesn't look like the same when we do it in another dimension?
Oh, that's like motion.
Yeah. So like
if you had something orbiting on a plane.
Yeah, but if it's orbiting on one plane, it will look like something, and if it orbits on another plane, it will look like something else.
Yeah. Are you saying something that looks uniform across all?
No. Something that looks different across 2 different dimensions, so that 2 different ways of Are
you saying that there is a fundamental that you can't represent something in terms of?
No, what I'm trying to get to is that if we in space, rotation in space is weird because you have a point that's going in one direction in space, and then it's going backwards in space, and it's going forward again, and you can't do that in time, as long as I'm aware. But something that you can also do in time, but...
What's interesting is you said as long as I'm aware.
Whereas
normally we say as far as I'm aware.
Well, as long as I'm aware, yeah.
He's already made the transition. He's just trying to get us to move. Oh my god, he's seen the other one.
It was interesting. I thought it was interesting that you said that.
I always say that. I don't know why. But I should say it's wrong, But
we live in a temporal world.
But I mean, like, something that.
I'll make that.
Wait, let's see something. Simpler. Like, I can think of something really simple, which is like if you shine light in this direction or if you shine light in that direction, then energy is going either in that way or it's going in that way. But so that's different between these two directions. So we need something similar to
but
this.
The assumption you're making here is times arrow, isn't it?
What?
The assumption you're making here is times arrow.
Well, the assumption that I made. No, I'm not saying that times arrow is constant or anything.
No, but you're saying that there is a direct.
There is a direct.
Like, how about if I throw a ball up
Mm-hmm.
and then the ball comes back down?
Mm-hmm.
But if you just stop it in the middle,
yeah.
Which way is it going? Do you know if the ball's going up or down? If I just took
No.
a snapshot,
I guess.
is that kind of what you mean?
No. What I mean is that if we're supposed to find other dimensions in space, how would you suggest we do that? In time, sorry.
Yeah.
In time.
Well, I don't think that. What do you mean finding them? Are we saying
Like you want to say that they
system.
exist? Yeah, you want to say that they exist. How would you go about and saying that to somebody who would, question you about it? Yeah,
So currently, our experience only has one dimension of time, and things move forward in time.
Yes, but our experience is expanded through labs.
Yeah, no, but I mean our daily experience.
Yes,
as in it's a case of there is yesterday, today, and tomorrow. It's not a case of yesterday can
one,
be
yesterday
tomorrow.
two.
Yeah, it's not like a closed loop or a closed surface kind of thing. We say it's a line.
Yeah.
And
but does this line splinter?
Either it could be a line, or it could just be the way we observe the universe has made us accustomed to seeing it as that.
Yeah.
So, if we're exploring that there could be more dimensions, then I guess the first thing would be to see what other directions we could go in time.
Yes.
And how would you test that would be... Could it be how you define direction in time? Now,
well, yeah, first you gotta do that, yeah.
Yeah, so could it be that your rate of
speed
time... Yeah, well, as in, so spatially you can
but that has an end, as far as we're aware.
How do you mean?
Like, your rate of time can get only so slow.
What do you mean, your rate of...
Like, your rate of time can increase or decrease depending on how fast you go.
Yeah. Well, your rate of velocity can go to zero.
Yeah.
You could not move. So
you could not move, so that's true. And then there's the other end, where time could not move.
Yeah, as in, this is what I was saying with the distribution of energy between space-time. So if you're going... So effectively, if we can never get at velocity, we can never reach the speed of light, then that means, say we got 99.9 recurring percent at the velocity
of
light, then... we're being like that again, saying we're not at one.
Yeah.
Then we will still go through time, albeit at a very, relative to now, slow pace. But we still make the jump. And then so basically what that kind of says is there always has to be a distribution. You can never have a complete up or down state. It's never completely in time or completely in space. So we could effectively do it the other way and effectively not move throughout the whole physical universe somehow. And therefore we go through time super quickly.
That's not possible.
Why not?
Because how do you not move?
No, but theoretically, let's say if the universe was kind of fixed.
Yeah, theoretically, I mean, how do you define that? What is it different from what you're doing now, with your experience with respect to me?
No, with respect to you, but I'm saying with respect to the absolute.
But that doesn't matter based on the principle of relativity. Of Einstein and Galileo, but Einstein. You know what I mean? I'm your universe.
Yeah, no, I get what you mean. Wait, no, but isn't it total though? Like, because technically I'm moving. So relative to you.
Did you say relativistic according to Einstein and Galileo?
No, I said Einstein, not Galileo.
Oh, I see.
Yeah.
I was confused about
Galileo was
what
way
Galileo
ahead of
did.
his
I
time.
was like,
The unspoken truth.
Exactly.
Actually, wait, because I'm going on this planet, which is going around the sun
Yeah.
very fast, and the
But-
sun's going about 220 kilometers a second.
Yeah.
And then who knows how fast the galaxy is? I think there are figures out there. But so you could say I'm kind of going at relativistic speeds anyway.
Exactly. But with respect to me, you're not.
But with respect to you, I'm not. So
So if you move with respect to me at relativistic speed, even if that means that you're constant with respect to the universe,
What does
then
it mean with respect to the universe?
I don't know.
I don't know if we were to say the universe, say we
Stop
like to the
moving.
universe as a fixed static thing for now. Let's just say, and that you could say, and then say I would stand in the center of the universe and not move. So like right now, you could say I'm orbiting around the sun, so I'm moving. The sun's going around the center of the galaxy, so I'm moving a lot more. And then the galaxy's orbiting with the local cluster or whatever. So I'm moving a lot more. So a lot of my total energy, we're talking about between like your temporal and your spatial energy, so to speak. My spatial energy has a significant value that I can't say it's all on time. I can't say it's negligible.
no, but that's the thing. It's this is weird. That type of energy is not invariant under Lorentz transforms. That type of kinetic energy, which depends on your reference frame.
Yeah,
So you don't have that energy, to me.
Yes. Okay, so if you and I are standing next to each other,
We would have equal
or like
amounts of-
now,
Yeah.
then- so you could say this is the fastest that we can perceive time.
Yes, exactly. That's what I'm saying.
Okay.
So, is it though? That's the question. So I mean, is there another way, somehow, to go backwards? I mean, like backwards isn't slower.
I just missed that reason as to why we're experiencing time the fastest that we can.
Okay, so you know how we say, I guess it's analogous to
If you want to use some paper.
kinetic energy or.
Yeah, you can do it with the triangle. Yeah, the reason why time dilation happens.
I know, I was just gonna do
I was just confused as to why you said that we're experiencing time the fastest that it can be.
Oh, because we are at zero speed with respect to each other, so there's no time dilation at all.
Oh,
So if you had,
right, I see. Yeah, sure. Okay, sorry. Yeah, okay. That's well.
I guess it's almost like the complex phase diagram of real and imaginary, and the magnitude is always constant, but it's just how much are you distributing in each. So say let's just say we're confined to this quadrant, then I could have, and say the magnitude of this vector is c, then I can never, let's say we can never go completely to x or completely to t, but I could have I could have a very strong spatial component and consequently a very small t component, gt dx. Whereas as such, so say when we're going towards relativistic velocities by our measure, i.e. high meters per second, and you can go up to here, and so the rate at which we go through time, dt, is very slow. And we say time slows down and then dx goes up.
Yeah. No, I think I think I sorry.
No, it's okay. So it's just basically saying that, so that c is always constant, but the proportion has to adjust accordingly. As one goes up, the other goes down. It's just an inverse proportion. So if we're going through, if we're not moving relative to each other, then our dx is very small, and therefore our dt is very high. And you can say it's, if you were to plot it as a gradient, it's at a maximum if we're both stationary.
Yeah, let's go faster.
Yeah.
Stand stiller.
Yeah,
Why are you moving?
exactly.
Stop moving.
And then
why do you want to experience time faster? Surely you want to
It's
experience it
possible,
slower.
But then if we start moving.
You need to anti-move. You need to.
Oh, but the thing is, if we're saying it's a circle, you can say as the arrow goes round. You get all the way there, and then when you come back,
The arrows.
you go to negative t. But remember, on this side, we're confined to that quadrant.
Yeah.
So if it reflects an x, if you take the magnitude of x, then you'll also be taking the magnitude of y.
Yeah.
But the fact is, do we take a magnitude of x, or do we say we're going backwards through space? Now, the way we've set up the coordinate system, x, y, z, we say there is a backwards. But that's only by convention. Not only, that's at least by convention. What if you could never actually describe?
What if you described your ultimate zero at the edge of the universe, or something like that?
What if you could never go backwards in space?
Exactly.
So, what if it's a case that time? So say, like we can have relative positions. So I could say you are both in front of me, relative to me. But then we could say one of us is going at a faster rate through time. I could still say, well, rather than you being faster, I could say they're in front of me in time.
Yeah.
Relative to me, that
person they're going slower than behind you.
So we could set up an arbitrary, like by convention, standards by saying they're in front and behind me in time.
Just like.
But it's just out of convenience of
that we're all mostly at zero.
Yeah, or as in you could say that we can never go back. As in, so if we say time has an arrow, why has space not got an arrow? Maybe it does. It's just because we're so used to.
But then we're ultimating an ultimate zero.
Yeah.
Of time, but rather than space doesn't.
Well, we say that was the origin of the universe.
Do we?
On Big Bang.
Yeah, but isn't that right here?
What do you mean?
Like this, if I'm right, space expanded, so that space is everywhere.
Yeah.
So it's not the same
but you
space.
say there was. But you could say that. I think I see what you mean. So if you had the typical diagram of space being a funnel, space-time being a funnel, that's inflation.
That's such an underrepresentation, though. But yeah.
Well, that's what
I know. That's what they do. That's what they do. Yeah.
So you could do.
Yeah.
Four-dimensional.
On 2 dimensions. Yeah.
Well, so if you think about it, whenever you have the drawing of a potential wormhole,
Yeah.
it's actually a 2D plane warping into a 3D funnel.
Yeah.
But try and visualize a 3D cube warping into a 4-dimensional thing.
Yeah.
We can't.
No.
As far as I'm aware, we can't. But
and
that's another interesting thing. Is it possible for us to conceive ideas in dimensions higher than that we are confined to?
Yeah.
Or is it just impossible? And if so, why? If not, okay. But if we're saying this is space, surely we're saying that's the origin.
Yeah.
And then we're saying it's expanded, so the origin has become everywhere. But we say it's expanded through time.
Yes, okay, if it's expanded through time, but then as you go back through time, the size of the universe gets smaller and smaller. And so if you're talking spatially, then if you take any point,
the same thing.
Yeah, if you take any point, that point it doesn't go away, it just gets closer to another point. And so,
But then, kind of almost like if you had the balloon, you could say a centimeter squared at time 0 is the same as, this is technically that centimeter squared at time 5.
Yeah.
But then you could, could you not say if you went to time, like current time, and took a centimeter squared, then played it back, it gets smaller then?
Yeah, that's the problem, because the Big Bang says that it started from a point, which is supposed to have 0 volume.
The whole 1 over 0.
Yeah.
Where it blows up.
So I don't know about that.
Well, what if
that seems like a very big inconsistency there.
So, like, say, because like you said, if we went back through time, so we're still using time as one of our measures there.
Yeah.
If we didn't take time and said, almost like I was saying that, what if it's an array of space with events, and time is the path we take through it? So effectively we flipped that my journey from mine to here, you could describe it spatially through time. So I went along the avenue, then after I traversed that distance through a passage of time, I took a right, and then I went around one corner. You could describe my...
But that's the problem. You have different options in space, but in time you don't.
By convention.
Is it?
No, this is what I'm saying.
Yeah,
what if that's the case? What if it is by convention? You know.
So yeah, that's a good point. Let's see if we can create a hypothetical event that happens and the cause and effect is the same, but it follows a different temporal path. Is that possible?
Yeah.
Well, you could.
Yeah, what does that mean? So, I mean, when you start to think in different temporal path, what does different temporal path mean? Does it mean
that you just go...
Okay, so let's think of time as change.
Yeah.
If we think of time as change, then it means that one thing happened, and then after a certain number of changes, something else happened. And those changes could be different changes.
Yeah.
And if there were different... So that's easy to think of.
Yeah.
So, like, I don't know.
But
you could get punched and fall down a building, you could get punched and shoved down a building, and you could fall in the exact same way.
Yeah.
That's such a grim idea, but anyway.
I'm confused, but then can you traveling in different... confused about, like...
Very good quality paper. It's very thick.
Did one thing right.
It's got high GSM.
I don't know what that is.
Grams per meter squared.
GPM.
Per square meter?
Per square meter, yeah. Because it's basically about how thick and strong it is.
Cool. Yeah, like would the events be? They wouldn't be spatial events. They'd have to be something kind of. I mean, because if you want to travel a different way through time, and you're saying you want different events along that journey, then you couldn't just say, "Oh, I'll go a different spatial path," because you get different events. Like as you say, you can get from A to B via taking a bend to the right or taking a bend to the left, and, and then like still converging on the same point, convex or concave kind of thing. But you need like something intrinsic to happen to something, rather than like going a different place.
Could this not touch upon principles of least time?
Yes.
No, because we have principles of least action. So, you know, when we first did the waves module here, you had deriving Snell's law and all of that, and you say originally they had the principle of...
I forgot something about
the refraction.
Yeah, and one of the actions is that light takes a path of least action. But before that, they thought it was the path of least time. So you could say that there were different paths. It was kind of effectively led on to the principle of least action.
It was different paths being taken, but the one that
took the shortest length of time is the one that light would take. But then they said not necessarily. It might...
It's because the other one's cancelled out.
And it's really the principle of least action. So what that...
But they're all happening at the same time and then cancelling each other out.
Yeah. But the fact that it's least action and not least time, potentially, I would say potentially opens the door for the possibility that light may not take the path that would effectively be the quickest as we measure it. Well, as we're confined because we're also limited by the speed of light, but it could be there is another path it could take that would be quicker in time somehow. I can't visualize it, but I imagine it would be quicker in time, however that's going to be measured, but requires more action. So whether that's a case of it has to, I'm not thinking this is the case, but for example, say it has to go through more material somehow. I can't.
But it's okay. So, but the way that I remember this
straight line, roughly, yeah. But then we see it like this, and it's completely different. And this is an example, a perfect example to prove my point. And I don't think it is possible because this is
space.
This is space. But it's almost like when you do, like if you do image manipulation, you can convert from rectangular to polar coordinates. and you can do polar to rectangular. Actually, you guys carry on talking. I'm about to do that. So I'm listening to what you're saying.
Yeah, what was I going to say?
Space.
Oh yeah. So I don't know if you ever read it, but there's a bit. Did you ever read The Strange Theory of Light and Matter? The Strange Theory of Light, I think. Well, anyway, it's a nice book. You should read it. Feynman.
Oh, okay.
Yeah, it's short. It's like
Oh,
80
really?
pages.
That's nice.
It's 80, and it's short as in small and short. So yeah. So in it, he talks about in reflection. He says, why is it that light reflects at the same angle that you do? And he uses that principle to explain why is it refracts. And he basically says that if you have a light source here and you have a receiver here, here, and everywhere, basically. So when the light, let's say the light sources go everywhere, and let's say that each of these reflects in a way that part of the reflection goes to the one particular source that we're looking at, right? So let's say that, for example, you have this source and you have this receiver, or this eye, or whatever, and light from here, there's one path that goes from the middle and goes up here. There's another one that goes from here and then goes that way. So it's not, it's not symmetric and that way. And he was saying that this path that goes there and that path that goes here, they cancel each other out because of their phases somehow.
Okay.
And as these lights come closer to each other, these phase differences become smaller and smaller and smaller until there's no phase difference when they're in the center. And he was saying that's why that we see it. Now, the way that this works, why is this true, is that this distance here and here apparently is not the same. They're slightly different. If I remember right.
Maybe. I don't really.
First of all, upon reflection, there is a 180-degree phase shift. Oh yeah, that was it. I think. No wait, was it that? Upon reflection, there's a 180-degree phase shift, and as you moved. Right. So it was like this. So if you're right, this is gonna be a little bit difficult to do with hands. But anyway, I say this, and my legs are the mirror.
Yeah, sure.
So when this light goes from here to here, and then this one when it goes a little bit further, as you change your position here, the phase changes a lot. Because the distance changes a lot. And as you get closer to the center, this change in distance based on how much you change in distance of the light traveled as a function of how much forward you've gone becomes smaller and smaller, i.e. what I mean is that as you start moving towards the center, each centimeter that you move towards the center contributes less to the phase change of your light. To the phase change of your light as it goes forward, right? So, okay, let me.
I was watching and I was like, "What he's explaining," and then I was like, "Wait, what do you?" And then you're just like, "Wait." I just watch people. That's what I do. I watch how people react to things.
I didn't understand that what you just said, but I did, and I'm confused about. I don't know about the distances of the different paths, whether they will be different. They will be, won't they? Depending on what. Even though they're just going from A to B, it depends. Even will it be different distance? I can't think of an easy way to think about it. Like I guess they will slightly, but they won't be radically different, will they? But what you were saying about like, I probably understood completely wrong. The reason we see, hang on, you're saying like if you shine a torch like that, and you have an eye here. However you draw an eye. How do you draw an eye like that? There we go.
Yeah.
I don't know. There's like an artistic way that they do it on science things. So
that is an eye looking at me from the side.
Yeah, the iris is pretty freaky.
Yeah.
It's
Yeah, I get it.
God, you know what I mean.
Yeah.
So the reason that we see the spot of light here rather than, but light doesn't go out there.
Well, he says that it does. He says that a bit of it does.
Like, I guess, yeah. So the reason we see it there is because otherwise this cancels out, and this is like effectively sort of dark fringes or something, or like
right.
Or whatever,
so
like,
the reason was
but then
that
surely you'd get like a pattern, then you'd see another spotlight here. If
yeah,
there was
yeah.
like a phase difference, and you just get like.
So what he was saying was that as you move this point from here to here, the change in length of the total length of this is much larger than when you move it from here to here.
Okay.
So if you have like 100 pieces here and why? Because as you get to the center, the it's like a the total
just the fringe pattern differences though, because
right,
the angle is proportional to.
So the total distance. The total distance from this plus that follows a function like that as you go from here. Does that make sense? Yeah? So as you are closer to here, this change is less rapid. And as the change is less rapid, it leads to constructive interference because it doesn't have time to become, to flip and cancel itself out.
That's very interesting.
Did you get that? Yeah, and that's why it's in the center. Otherwise, it is supposed to be everywhere. So, for example, if you position dark fringes in the mirror where at certain distances to each other, you would see light reflecting from all of them because they won't cancel each other out.
Wait, did he actually do that? Right?
Yeah.
Oh, wow.
Yeah.
Hang on, what you're saying? He did actually see these.
What? No, if you don't have a complete mirror and you put dark fringes at certain places of the mirror, then you would see the light like reflecting from there a little bit.
Sorry, I'm a bit tired. I didn't follow you again. If you did have what if you put dark fringes?
Yeah, so you have a mirror. Say your mirror is not completely. No, that's right. Yeah, say your mirror is not completely like mirrored like that. It's got dark fringes in between it. The mirror itself. So the mirror is non-reflecting at certain points.
Oh, I see.
Right,
okay.
and if you choose those points somehow, that it's the points that would cancel out this one, then what you see would be the light reflecting from here and here and here and here and here, rather than just from the middle.
Oh, really? No.
Yeah. It's in his book.
Yeah. No, that's why I was like, wow.
Yeah.
Sorry, like 2 hours later, Kenny's dropped.
Yeah. I mean, he says that they've done that experiment and everything, so.
I didn't realize.
Yeah.
So we were talking about that with. Oh, that's kind of cool. I was talking about that one night when I used to live with another PhD student in physics, and we would like talk about why does light choose this path and not the other one? We don't get it, and it would puzzle me, and I'd be like, oh yeah, that's really exciting. I go to bed, I go to work, and do something else that's really boring, and don't ask my supervisors. That's cool. I wish this is what PhDs should be about. They should just be this constantly.
Does that look like a straight line?
Yes.
Which bit? Okay, that's like yeah.
I made the line thick, so it looks a bit.
It's like a straight line going into the page.
Or what do you mean? Or what do you mean? Like, is it there's like either lots of lines converging?
I don't know. I'll just make a thinner line.
Oh, okay.
I made that thick just so it was visible, but.
Oh no! Okay. We can imagine that straight.
But it's a triangle.
It's like, but it's not.
But it's a triangle.
Like the king is wearing clothes. No, but
oh. That's so cool. That's so weird. But why would you?
Because light does that in secret.
So this one, but this stuff would have to cancel out with this stuff. So you'd have to put non-mirror here.
No, not necessarily. They cancel out with the ones next to each other.
Oh, really?
So, for example, this one. This one. Okay, this is the optical path here.
Yeah.
The optical path here, and this is just the position that the reflection is happening. Yeah, so these are the points on the mirror, and this
Yeah.
is the optical path.
Yeah.
So here, the optical path is this much, and on the next point that we
it's
put,
just-
the optical path is this much. Now this may be an integer number of wavelength,
Okay.
right? So this distance,
Yeah.
basically,
Okay.
that.
Yeah.
But as you come closer,
Yeah.
after a certain point, like for example here,
Mm.
this is smaller than one wavelength.
Mhm.
So anything that hits on these points will not be able to destructively interfere with itself. So you'll see it when it comes out.
But I'm just confused about where you put. So you put the fringe. So you have to work out.
Oh yeah, you
like
have to work out those things. Yeah.
Okay, so you'd have to do like I don't know, put a black bit there and a black bit there,
Yeah,
or something
like that.
Okay.
And you'd also, I think they didn't do it with light. They did it with like radio waves or something.
Okay.
Yeah.
Okay. Nice. Nice.
Yeah.
That sounds like a good PhD.
Yeah.
And now we'll get rid of them. There are lights everywhere. Oh my god.
Yeah. Okay, that looks pretty straight.
No, that's
a straight line.
Yeah.
This is in rectangular coordinates.
Yeah.
Now, if I put it...
What are rectangular coordinates?
Oh, just x, y, z Cartesian coordinates.
Okay.
But if I represent... Now this, what is that? Is that a curve?
It's like r equals theta or something.
Well, that's just a curve.
Okay. No, I mean, is that what you mean?
Kids,
No,
what's
no, no,
this?
I
It's a circle.
It's r equals theta, actually.
But, so you'd say that's a curve, yeah?
Yeah.
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 You wouldn't represent that as
No.
straight.
Yeah.
So to describe that in x, y, z,
Yeah.
you'd have to do something like r
fancy.
equals x squared,
Yeah.
but let's say it went around the whole thing. But if I convert that from, so according to this dimension, so to us it looks curved,
Mm-hmm.
and you could say an observer's going along this path,
Mm-hmm.
and they say, no, it's straight.
Mm-hmm.
But to us as observers, like, no, you're going practically in a circle. Like, no, I'm going straight. And then they go,
They're
that's
looking
the
at it
path
from the
they
side.
see from their point of view. And that's just converting from so this is rectangular. So I just said go from rectangular to polar.
Yeah.
And so if I did that path, if I drew that path first, then they go from polar to rectangular,
Mm-hmm.
it becomes a straight line.
Yes.
So this was the point I was trying to make about how we say x, y, z,
But
and
it's
we
like
could say
this.
I've gone forward, then right, then forward, then left, then turn 60 degrees, etc. And effectively, it would be a very complicated coordinate system, but you could, I would say, I'm imagining, for any path that you take, you can come up with a coordinate system that represents that as a straight line.
Yes.
So, surely the same could be done for time.
The reverse,
But-
you mean?
Otherwise,
Because time is
how we
already
say
used.
infinite dimensions.
Yeah.
But
Yeah.
then this is going with, well, can you
But
still
what we
move forward? And, what are dimensions in time?
Yeah.
So we can say, so
We have to
effectively-
set something.
Well, yeah,
essentially.
effectively, because if we say this is a straight line, you can say there's no need for any other dimensions other than one.
Yeah.
And it's just when you differentiate things that you see there are other dimensions, so to speak, that you can say, well, if it was at an angle, you could say, well, like technically you could say this at an angle, but you could say, well, as x changes, y changes, as x changes, z changes, so you can differentiate it, but effectively you could come up with any coordinate system that makes it seem as if there's just one dimension that it's going along.
Yeah.
So I would say at the very least this opens up the possibility that
That time has more dimensions.
we see time as just having
One dimension.
But but on the converse, you could say we're trying to differentiate time. Or you could take it the other way, or why don't we try and integrate space into one dimension?
Into one dimension of distance.
And for us, it's easier to differentiate space, and therefore,
We've done it.
yeah, and so we parallel it to, we try and apply that same reasoning to time. But, and I'm not saying not to pursue that. It's very difficult in my mind. That doesn't mean I wouldn't try, and I'm not going to try. It doesn't mean I'm not going to try. But then, also, I'd say worth considering is that if we're saying that time and space have inverse relationships in terms of the way we go through it, could it be that any function we apply should be the inverse to actually make sense of it, or as in to make it
Yes.
intuitive? So with space, we try to differentiate it, whereas time, it could be that we intuitively differentiate space. So it could be that, therefore, by inverse.
But we do intuitively integrate time.
Yeah, no, that's what I mean. So we see time as one dimension, but if we try to integrate space into one dimension, if we try to explain all of this in terms of quantities along one dimension, as in, I'd say, basically, I guess what I'm trying to get at is that I think it would be a paired thing, that if we ever came up with a system, whether we do this now or not, if we came up with a system that
Ridwan's for president, he's going to say we're all going to have to live in a different system. No more time. Harmony.
Yeah.
Sorry.
There'll be no change. No, there's change. No change. No. I'm kidding. But it could be, I don't mean this probably isn't pursuing the actual thought train. This is more of a commentary on if we did pursue it. That I imagine if we could differentiate time and actually work in that framework, in that mindset, we could probably quite easily, once we've hacked the maths of that and the perception of that, we could do the inverse for space and integrate what we typically see as 3 spatial dimensions as one integrated spatial dimension. That's just a commentary on it. But now going back to the actual thing of can we differentiate time, I say probably. If we can do it for space, because like our maths, well, in this country at least, you start off on 2D kind of thing. I mean, in fact, you even start off on 1D, and then you go to 2D, and then 3D. And then we talk about changing coordinate systems of polar and cylindrical and spherical. So we're capable of manipulating it. We have come up with mathematical systems to go with higher spatial dimensions. So
it should be able to add on to the time ones.
Like through reciprocity. If we can go to higher spatial dimensions, we should be able to work it back down to 1. And
increase
on converse, we can do time.
Yeah, hopefully.
Minimalist in new fashion. Yeah. You want to make more and more dimensions, or everyone just wants to write one?
Why everything simpler if it's like a grand unified theory?
Yeah. Why are we saying that space and time are the inverse of each other? Because of C? Or because of...
Yeah, because of C.
Is that the only reason?
That's the only one suggested now, but it doesn't have to be the case. There could be others.
But I mean, what if I don't really like C. I mean, it just seems a bit arbitrary, doesn't it? I don't know. Well, I mean...
It could be arbitrary to us, just to be 3 times 10 to the 8, which doesn't seem like a very...
No, I know. It's just, I mean, why light? Why not... hang on. Why not something else? I don't know.
The speed of sound.
Well, no, I don't know.
But you can say light is a transfer of energy, and if we're saying that the whole universe is energy, as in everything we perceive as a measure of energy.
But what actually moves when you've got photons moving?
So technically a wave is a transfer of energy.
But
so if we've got a photon.
But it's
I've got a problem with photons. The other day I was in the bar and the photon comes in, I'm like, what the hell?
We were talking.
Yeah.
You can talk about it here. You can talk about it.
Like sheds light on all my problems.
You were waiting.
I've been all night. Somebody says photons.
It's like, everyone mentioned this knowledge cafe. It's the perfect place I could use this joke. Now we just have to wait for a situation.
I know, I'll just get them talking about what's an easy way to start this joke in. I know, we'll talk about time having more dimensions. That's an easy way to start this.
That was the biggest setup for the joke.
Oh god! But with the thing, okay, this is what I was gonna say. With time, with photons, photons essentially observe the world, I think, in one dimension. Because if they
stop imposing your views on anthropomorphism onto photons. Carry on, sorry.
Oh god, I'm a
What was that
photon
long word?
dictator.
Anthropomorphic.
What's
Because
that?
you know when you say that, like when they say, why does an electron emit energy when it's excited? Because it wants to be.
Yeah.
Yeah, so the thing is, there's so much length, there's infinite length contraction when a photon is moving, because it's moving at c. So it sees it, to it is not moving.
Yeah.
Because, it's like...
The world revolves
But,
around me.
but isn't that right? Just so do they just move through time?
That's assuming we're
Right,
still
isn't
going on
it?
a...
But they don't, because, like, if they're moving through time, then they're moving at no speed.
This
I
is
see.
assuming a continuous
So they're
trend, though.
static. Okay.
Yeah.
They're static in time, right? The other way.
So
They-
if they're going at the speed of light in space, according to that diagram.
Yeah. Then they are,
Let's give
like...
it a name.
They are everywhere. Once they're emitted, they are everywhere in that dimension, in that direction that they're going.
Which I think is quite
Which is
cool.
weird, because then
But it makes
what's the
sense,
difference between a photon moving that way and that way?
though. It's not.
It's
It's
space.
just times arrow.
No.
That was so bad, man.
I know.
I love it.
But, like,
Bad joke, souls.
what's the difference in terms of length contraction? I mean, if I'm a photon, I'm going from here to that wall, then this entire dimension is 1 point to me.
Mhm.
So what happened?
According to our, nothing according to you, according to our, as observers.
But
we
I was
see-
created and destroyed. Oh no, I wasn't even created. I was only okay.
You weren't created, you weren't destroyed, you're just there.
I was
You
I was
always
just.
will be,
This
and
is
you
weird.
always
Oh
will.
god.
No,
Okay.
but surely, like, you have a light source. I mean, like, these light bulbs. So like a photon was created, right? Somehow. I don't know. What?
Well, I think, yeah, because they were transferred into a... Yeah, okay. Okay, so
don't-
energy
Okay.
wasn't great, yeah.
There's a much easier way of thinking of these, and it's in terms of waves.
Mhm.
Yeah.
Tune in next time.
No, because
Join us next
Because
time.
no. Yeah, actually, yeah, we should probably go. It's like 11.
Yeah, it's up to you. I don't mind.
No, I should
You know
definitely
can
go.
carry on until-
Yeah.
Yeah. No, I should definitely go.
Sorry, I shouldn't have waved at you. You know.
I didn't notice you waving it.
I apologize.
But
Right.
that's interesting. I want us to I want there to be a conclusion.
yeah,
I'm
There
gonna
is
tune
no
next time.
conclusion. You just
There's-
carry
yeah,
on, and
this
then,
is- No!
and then someone says,
Next
should
morning
probably
was
head
like,
off.
Yeah.
no, it's just like it will just look like right. I should probably head off, and then it will kind of just
Yeah.
but photons like
fizzle
me
away.
too.
asymptote,
But have you
like
read
a
that?
toilet roll.
Oh god,
Seriously, I'm gonna look into that. I think.
I don't understand the fascination.
We're
I
gonna go
don't
to
really
Sainsbury's and see if they have any.
Well, they got
infinite
that
toilet
whole
rolls.
aisle.
The massive.
Apparently, Sainsbury's had like their cookie
Frictions?
sale yesterday.
Really?
David Jelani.
Don't they
from
always
Cooks,
have cookie
I need to
sales?
check that
I
out.
want you guys to go along to a wholesaler and be like, "Do you have any frictionless toilet paper, please?" Like
Like, what do you
smooth,
mean?
smooth
What
toilet
is-
paper. We have
Our
carrots.
charming is very, very soft.
It's very
But I can
soft.
see
Yeah.
that the ply pattern on it is non-symmetrical. Therefore,
Yes.
that's going to introduce a lot of uncertainty.
I'm from NASA. We're looking for a new experiment. So a toilet roll for
It's
really.
approximated of
God.
just plastic sheets. Like, that's probably going to be really unhelpful. And
Yeah, if they're frictionless, they're not gonna work. Oh god,
Slips right
that's
off.
like a nightmare. You're like this
Oh,
is
yeah,
still
yeah.
clean. This toilet paper is still clean, but
Teflon coated toilet paper.
because you won't be able to wipe anything off with it.
But if it's frictionless, then they won't even stay in a roll, will they?
Yeah, that's the thing.
Yes.
So
You
no.
just pull the roll, and it could. If it had a. If
It has to be attached.
If it had a mu
You have to make a hole in it.
greater than
Hold
1.
it.
Wait, no, hang on. The mu coefficient is between 0 and 1.
Muco.
Right?
The
Mu.
mu-
Oh,
The mu
Jesus,
co-
we
The
didn't
mu
learn about that.
coefficiency. No, the mu coefficient.
Yeah,
You know when you
there are
do
two of
friction.
them though.
Oh, but as in, so for friction.
The static friction, and then there's
Dynamic.
Oh,
dynamic.
I don't
Oh,
really
you-
know
But
Yeah,
is that a case of 0 between 0 and 1?
yeah,
They
there's
might-
between 0 and 1. Yeah.
And so if it's less than 0, what
Then,
if you had
no, if
toilet
it's
roll?
0, it's
What
frictionless.
if-
If
No, no,
it's
but
less
what if you
than
had
0,
toilet
then it'll
roll that
move without.
What if you have an
No,
imaginary coefficient of friction?
Oh my god.
Well, there probably is. There probably real and imaginary coefficients.
That's
true,
where
like,
the aliens lie.
But what if the imaginary stuff
It's
applied
direction.
to all of the antimatter.
What?
What if imaginary?
No, but the antimatter one, we can use our own math with the antimatter ones. Just change the charge.
But the thing is, you know how we say
Oh,
Well,
antimatter with interaction with matter.
no, like
No.
because you know how they say, well, you'd expect, I guess. Well, you could say this is us imposing our views, but you'd expect perhaps that the origin of the universe would have produced equal parts matter and antimatter.
Yeah.
But then that would either all annihilate, or if we're going on a very simplified, let's just say a 2D model, then you'd have opposing, almost like a dipole. That you'd get the middle bit should just be clear because that's cleared out from interaction. But then you just get one portion of the universe. What if
So you
all of this is matter and the
that's what I
same
was
things
gonna
happened
say,
Yeah.
on
But
that side
surely-
and antimatter, and the wave functions have been going through the whole time? That we take the real part because that's what we observe.
Yeah. Oh,
But if you
God.
think about it, if you neglect the real part and just take the imaginary part,
Then it'll be.
effectively you would have a kind
No,
of
but the
similar-
imaginary part doesn't have the same form. Usually.
Yeah, well, that's the units of time.
No, wait, it does. It does.
Well, because that's just a phase argument,
Yeah.
and because k is inverse of x in units and omega is inverse of t. Yeah, because the phase argument is dimensionless.
The phase argument
sorry,
is.
no, as in the whole argument.
Yes.
Kx is per, well, like say in our problem, it's per meter times meter
Okay, yeah. The whole thing
per
is.
time per
Yeah.
second times time.
Yeah.
So the argument, so it could. What if? Who knows this? But what if
Yeah.
the real part is what we take?
It's
And-
like you've been ruining physics
No,
for
no,
generations.
No, because again,
You always
think
take
of it,
the
it's
real
just by
part.
convention that we name these things
Yeah.
as such. So what if we just happen to name the real part the matter part?
Yeah, and then
And then the imaginary
the
part
other
is,
it's still quite.
I
exotic.
can't rule it out, and it might be observed, and this could be just complete cowboy physics, mathematics.
Yeah.
But
I
it
like
could
cowboys.
not be.
Yeah.
It could be. So what if that imaginary part still applies? Because that's the thing. Where does the imaginary part go?
When you were saying about the omega and the imaginary part and stuff, you were talking about the wave, like a wave function of a atom, right? When you,
Oh, just,
Yeah, sure,
yeah, just general.
yeah, of course.
Yeah.
Well, that feels like a nice conclusion if there's any.
Yeah.
But I didn't.
that feels right. That field. I like. Right, I'm going to call a taxi.
Sure.
Is that how you got here?
Yes.
Oh wow. Okay.
How long did it take you with a bike?
10 minutes.
Okay, yeah.
Oh yeah, it takes about half an hour to get to mine. Doesn't it?
Yeah.
Yeah. I was wondering how you get here.
I was gonna walk.
I thought you would just bus or walk it.
Yeah. Can you bike? Is it
Or
a
you
bus
could
nearby?
bus to the avenue.
No.
And then walk along Hill Lane.
You can't-
Walk along Archers Road to here.
Yeah.
Oh, but you wouldn't be able to get a bus from the avenue
Yeah.
because you need to use 6. Press. No, just hold. Press 1. No, press 2 for lost property.
Yeah.
Yeah.
Press 1 if you heard me right. No.
I guess we don't
I
need to
know
record
you're
your
doing that.
taxi.